Hey guys, it's Terry again. I got an excellent question last night dealing with IP CEF. The student wanted to know, how does IP CEF work? Well, to address how IP CEF works, what we're going to need to do is, just like always, we're going to have a network. You can see it on the screen. We've got R1, R2, R3, and R4. They're going to be interconnected all with fast Ethernet, and we're running individual networks. Now, the reason that I've got the link between R3 and R4 written in blue is because I'm running EIGRP on this process, or on these devices, EIGRP AS10 specifically. Now, when we're talking about CEF, we first have to talk about our normal, everyday layer 3 routing table. Now, the reason that we're going to talk about it first is whatever is inside of our routing table is going to drive what's inside of our IP CEF tables. And there's going to be two tables that we're going to talk about when we deal with IP CEF, and that's going to be the forwarding information base and the adjacency table. Now, I'm going to bring up a piece of equipment. We'll bring up R3 because R3 is connected to R4 via EIGRP. We can demonstrate that with show IP EIGRP neighbors. We can see that we're connected to R4. Let's take a look at our routing table. Show IP route, and we'll specifically say EIGRP. Now, I've got a whole bunch of IP addresses that are being advertised into EIGRP on R4, and they're using various and sundry different address ranges. So then get a mix here to demonstrate the fact that our routing information base, our RIB, that's what we're looking at right now. That's the contents of our routing table. Has all of our prefixes in it. I mean, we could ping any one of these prefixes on R4, but the problem with this is the fact that this table is in no real sequential order. So let's say we were trying to route out this interface right here. We were going to try to reach this prefix 15.66.0.0. Well, we know we're going to go out FAO00. It only makes sense. That's pointing to R4. But to find that, we would have to parse this table all the way down to the bottom. So that would be what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, more than 15 individual lookups to identify this prefix so that we can route to it. The key item here that's given to us by IP CEF, and IP CEF is enabled by default on our devices, show IP CEF, is we have that forwarding table. Now, if we're going to use the forwarding table to send information from point A to point B, we're going to parse it instead of the routing table, and we can look at the contents by using show IP CEF. Now, it's going to be plainly evident that the forwarding information base, the table, the IP CEF table, is much better structured compared to the routing table. Based on the way this table is arranged, everything is organized from 000/0 all the way down to our broadcast addresses. So rather than having to parse this table 100 times to find a given prefix, what we're going to do is we're going to parse it 4 times. We're going to look first for the matching number in octet 1. Then we would look for the matching octet in octet 2, then we would look in 3, and then 4. So ultimately, to find any prefix contained in the forwarding information base, we're only going to have to perform 4 lookups in the table, parse it 4 times. So that's going to make things a whole lot more efficient. Now, it sounds strange to get excited about this in the context of our routers, but you have to keep in mind that it's IP CEF that gives us the abilities to do things like NBAR, network-based application recognition, which we'll discuss when we cover QoS in detail. But the fundamental element here is that it is an optimization. We now have the capability of reducing the strain placed on the CPU to conduct forwarding But another element that we have to look at is, remember, I mentioned that there was two tables. There's the forwarding information base, showable again with the show IP CEF command, but we also have the adjacency table. And we can say show adjacency. Now what I'm going to do is I'm going to specify detail because I want to look at the whole contents. We'll first go ahead and just use it without the detail command, and you can see that we have these addresses that are adjacent to us, and there's not that much associated with them with regard to detail. So let's use the detail keyword. When we use that, we're going to see a whole lot more information. For instance, we're going to see what we saw previously, but we're going to see the number of packets that have actually traversed. We are going to see this designation here called epoch. The epoch is the number of times this table has actually had to be recompiled. So for instance, we can do a clear adjacency epoch, and we'll just say all. Well, I don't even think we'll have to say all here, and we should be able to re-execute this command, show the detail, and you'll see that the epoch has actually incremented by a value of 1 for these, and that was because we cleared the process, and by clearing it we forced the adjacency table to recalculate itself. Now there's another element that I want to point out here. This line item, this field right here, represents the MAC addresses that we're going to use to communicate. In fact, it's 2 MAC addresses. If we were to go to R3 and do show interface FAO, and we want to look specifically for the MAC address, we could do that most easily by using the include burned in address, or BIA, and we'll see here that we have a MAC address of 0014 A8FD1770, and we can see that right here, that value, we're seeing it in the table here. Now in addition to this, we can also take a look at the other end. For instance, we're connected to R4, so let's do the same command on R4. Exit, do show IP, do show interface FAO1, and we want to restrict it specifically to the burned in address, to the BIA. Oh, I did do. So we see here it's 04, we'll copy it and then we'll come back over to R3, and we'll just place it right here for the time being. We see here that the address that we're working with is sorry about that, guys. I was actually looking at the wrong address. We can see here 0014, but it's 1770. I was looking at 1771. So here is the source MAC address, and our destination MAC address is listed first, and that's the MAC address that we saw on R4, which is here. Now the next question is, well, what are these 4 digits here? Well, remember, 0800 is going to be our ether type for IP traffic, for Ethernet. So what we've seen here is that in the adjacency table we have all the information that we need to be able to perform encapsulation. So between the creation of the forwarding information table and the adjacency table, we have everything we need to have our devices perform switching. Now in a router, that's not going to be that big of a deal to us really when we think about it, except for the fact that it is relieving pressure and strain from our CPU, and it's taking things off the back of having to parse the routing information base, which in large networks where we have a lot of routes, especially where we're repatriating the BGP routing database and everything, that's going to definitely cause us to slow down, and CEF overrides that problem and fixes it. But on a switch, we have to keep in mind that the forwarding information base and the adjacency table are stored in hardware, and that hardware capability is what lets us function at wire speed on switches. But keep in mind, for things like network-based application recognition, we need these features to be able to run on our individual routers. Now, what I'd like to be able to do here is I want to go over to R2, and I want to make certain, let's see, show run pipe include CEF. Let's make sure CEF is on or off. It is actually running on this device. So let's take a look at the individual interfaces. Show run interface FAOO and FAO1. Alright, this is what we're going to work with here. We're on R2. We are running IP CEF, and we're not doing anything with regard to our route caches on our individual interfaces. So if I go over to R1 and I ping the address of R3, 10.1.23.3, and let's do a repeat count of 5. No, do a repeat count of 10. On R2, we know we have reachability, so let's do a debug IP packet. Now, I'm not running routing protocols on these devices. If I were, these devices would go insane. What I'm doing is I'm doing static default routing on R2 and R3 through on R1 and R3 through R2. So I demonstrated the fact that I had reachability. Now I've actually enabled the debugging. So let's go here and do 10. And let's run over to R2, and notice that we don't have any information coming through to us with regard to the traffic traversing our network. And the reason being is because we're working with IP CEF. So what I want to do now is I'm going to turn IP CEF off. Remember, IP CEF is on by default, so no IP CEF. Now the moment we do that, let's see if it makes any changes. Do show run interface FAOO. Let's see. Nope, nothing's changed under either of our interfaces. Do show debug. Let's make sure that the debugging process is still on. Yes, we're actually running the debug. And now let's send the 10 packets. Now notice we have traffic on R2. Well, what's happening now is we've routed via the rib 1 packet, but we sent 10. Now, the reason being is we've turned off CEF switching, but we're still operating using fast switching. So what we'll do is let's go to the interface FAOO, and let's do no IP route cache and turn that feature off so that we know beyond a shadow of a doubt that we are going to be doing process switching. Now, process switching means that the CPU is going to have to touch every individual packet that traverses through this device and re-encapsulate it, and that's going to take CPU capability. So what we'll do is we'll run another 10 through here and see what happens. Let's get some distance here. Let's do that, and then we'll run our 10 ICMP echoes. We'll go over to R2, and now we see that the CPU is having to touch each individual packet that we've sent. Now we sent 10, but based on this output, we're going to see 20, because not only are we going to see the packet coming through R2 to reach R3, we're going to see the packets coming from R3 back to R1 as replies. And we can see that very clearly when we just take a look at this idea here, where we'll just send 1 packet. So right now we're sending sourced from 10.1.12.1 to a destination of 10.1.23.3. We're going to forward it, and then we see the return sourced from 10.1.23 to destination 10.1.12.1. So with this enabled, and the other thing that I want to do is, let me just turn off timestamps. Config T no service timestamps. So we'll repeat it. This should give us a much cleaner output, which it does. Now, right now I am debugging IP packet. Let's hit IP packet and specify detail. Now, what I'm going to do is I'm going to repeat this process just using 1 packet. We'll get more output, but this is going to give us more information. We can see not only that we're sourcing from R1 destined to R3, we see our ICMP type. Type 8, that's our request. We can see the fact that we're getting information source from 23.3 all the way back to R1, and we can see its ICMP type is 0, which is our reply. But what I want to point out right now is the fact that notice that this entire process is going to be routed via the RIB, the routing information base. So if I were to send just 5 packets, we'll get 10 here, but each one of them are going to be forwarded. Both the outbound and the return traffic are going to be routed via the routing information base. So let's disable that behavior. Let's turn Ip Sef back on. Do show run interface FAOO. Now that's what that's going to do, is that's going to turn off or remove the commands that we entered under the individual interfaces, FAOO and FAO1. So let's go back and re-enable that just for Ceph. So interface FAO1 or OO. We're going to do no IP route cache. We'll just do it for everything. Cache. Because what will happen is you're going to notice here, do show run interface FAOO, we're going to see the command we entered, but it's also going to do the no IP route cache command for our Cisco Express forwarding. So what we'll do is do the same thing to FAO1, no IP route cache. Now what's going to happen when we come over here and do a ping? So let's just ping with 1 and see what happens. Do we get any output on R2? Yes, we're getting output on R2. It's the same thing that we were getting before. We're seeing our source traffic, our 10.1.12.1 going to destination 10.1.23. But notice here, it's now being routed via the FIB, the forwarding information base. And if I were to come over here and I were to repeat this process 10 times, we're going to see 20 of these messages, and every one of them are going to be forwarded via the FIB. Or excuse me, routed via the FIB. Routed via FIB. Routed via FIB. So when it comes to routers, think of Ip Sef as an optimization, to take the burden of having to do a lot of this encapsulation and this parsing of the routing information base to be able to accomplish encapsulation. So it's definitely an optimization. But when we look at it in the context of a switch, and we'll probably do that later on if you guys want me to, when we think about it in the switch, not only do we get more features, we have to understand the fact that this FIB table and the adjacency table is cached from the routing information base, but it can be stored specifically in the ASICs, in the application-specific integrated circuits on our switches. And that's the reason that the commands are slightly different. For instance, if we go to a switch, like SW1 in this instance, and we do Ip Sef, and we hit enter, it's not going to work because it's an incomplete command, because switches have ASICs. So here if we press our question mark, we can see that we can specify this notion here of distributed, and that's what we need to do. So what's going to happen is the cached information that we're calling our Ip Sef table is actually going to be distributed to the individual devices. Now I'm not running IP routing, so this is running purely, Ceph is taking stuff out of the routing table, and without a routing table we can't create it. So I can go in here and just like the iOS is telling me, do IP routing, turn it on, and then when I do Ip Sef distributed, it'll take, and I can go in here, exit, and show Ip Sef. And we can see the results. We're not running any routing protocol, and these are going to be seen on just about every device. Now, when we go into and discuss the foundation bootcamp, where we're talking more about the actual application, and you as students are doing more console stuff, remember, this is preparation just for the written. We're going to learn more about the receive, the drop, and things like that. But we'll definitely be talking about that in the context of MPLS when we reach that particular class. So this should explain to everyone why and how Ceph operates and works. So with that done, I think I'll get back to working on labs. You guys have a wonderful time, and thank you for your time and attention. Bye-bye.